Greetings, parasitologists. We're back to look at the results of our study, which tests whether conservation in the form of increasing biodiversity and increasing forestation can protect people against parasites. Okay, so let me begin these results just by getting you oriented. It's important for you to be able to interpret what each of these tables mean. These results come from our spatial analysis, which you'll remember has its problems, right? Looking across countries, lots of things can be confounded with one another. And then there's our temporal analysis, which we believe gives us a little bit more flexibility to make inferences about what factors are related to what. So let's put these results side by side. Don't try to take this all in at once. We're going to walk through these results. On the y-axis of each of these tables, you're going to find all of the infectious diseases that we tracked. They are ordered from the most to the least burdensome, with the zoonotic diseases up on top and the directly transmitted diseases on the bottom. On the x-axis are the various factors that we included in our statistical model. So the things that we thought would be related to the burden of these diseases: wealth, urbanization, population density, temperature, rainfall, forestation, and biodiversity. You'll see that for both the spatial and the temporal analyses. The other thing that you'll need to know is that each one of the cells in these tables is a coefficient from our statistical models. If there's no coefficient, that means that that particular factor was not important in determining the burden of the corresponding parasite. Each of these numbers tells us whether these two factors, malaria and population, for example, are negatively or positively correlated with one another. If they're negatively correlated, they're colored red. If they're positively correlated, they're colored blue. So we can see, for example, that Echinococcus has a negative relationship with wealth. Wealthy countries have less Echinococcus. Makes sense. With that in mind, we can just sort of scan our eyeballs over the colors and see that there are a couple of common patterns. In the spatial analysis, we see that poor countries tend to have more infectious disease. So we tend to see lots of red in that wealth column. The more wealth you have, the less infectious disease you have, a negative correlation. Similarly, the more urbanization you have, the less infectious disease you have. The hotter your country is, the more infectious disease you tend to have, so that's a positive correlation. And we also see a positive correlation in general with biodiversity. The more biodiversity you have, the more infectious disease you tend to have. But those are just the spatial correlations, right? We already knew from previous studies what these patterns were. We knew that low-latitude countries were poor, hot, and tend to have high biodiversity and high infectious disease burdens. We already knew that. The temporal analysis is really where we start to see some new and interesting things. We see again that in the temporal analysis, in general, as wealth increases, infectious disease declines. As urbanization increases, infectious disease declines. We interpret the table a little bit differently for the temporal analysis because in the temporal analysis, it's about change over time. So for example, individual countries where wealth increased tended to see a decline over time in their infectious disease burdens. Individual countries where urbanization increased over time tended to see a corresponding decline in infectious disease burdens over time. So that gives us a little bit more confidence that this is a causal pattern. We also tend to see that forestation isn't all that important for a lot of these diseases, but where it is important, forestation tends to be positively associated with disease burden. Biodiversity is pretty unimportant. Only 2 diseases responded to biodiversity, one negatively and one positively, so one consistent with the dilution effect and one not. Now, if you're interested in any one of these individual diseases, you can kind of drill down into the row for that disease and see exactly what the correlations were, whether that parasite responds positively to urbanization or negatively to biodiversity. And I encourage you to look through the table and try and see whether the various correlations make sense to you, given your knowledge of each of these parasites. Pause the video now so that you can examine a few individual parasites and see how they respond to each of our factors. Okay, you've looked at the results for individual parasites, but if we want to summarize over all of them and ask what the generalities are, we can look at it like this. In this plot, I've arranged the spatial result on the x-axis, that's the mean effect of a particular factor, wealth, urbanization, whatever, on disease burden in 2010. And then on the y-axis, I've given you the temporal result, which is the mean effect of the factor on change in disease burden from 1990 to 2010. What does that mean? Basically, anything that falls into these two areas, those are results that we're going to have a lot of confidence in because that's where the spatial pattern and the temporal pattern agree with one another. These are results where we get agreement between these two very different methods of looking at the data, and therefore results that we're going to tend to have a lot of confidence in. Let's take a look. Each dot that I'm going to show you is a summary across all of the different infectious diseases that were included in this analysis, all 24 of them. What we see is that urbanization is the only factor that is significant in both the spatial and the temporal dimensions. It's the case that highly urbanized countries tend to have less disease, and as you increase urbanization over time, you tend to get less disease in response. Wealth is almost there. Wealthier countries have less disease, but increasing wealth over time doesn't significantly decrease disease. Close, but no cigar. We don't see a lot going on with rainfall, not much going on with population, and we already knew that hotter countries had more disease, but it doesn't appear that increasing temperature over time actually increases disease burden. This is probably because there are some diseases that increase in response to increasing temperature and others that decline, and they sort of just cancel one another out when you summarize over all of those diseases. Then we come to forestation. Now, what you can see is that as you increase forestation over time, you tend to see an increase in disease burden, which is exactly the opposite of what the dilution effect predicts. Now, think back to onchocerciasis, or river blindness, the disease where if you cut down forests, you tend to see far fewer cases. We've seen a number of examples throughout the series where nature is offering a disservice, where increasing forestation puts people at risk, and that's what's reflected in these data. Then finally, we already knew from the spatial analysis that more biodiverse countries tended to be those with lots of infectious disease. But it looks like increasing biodiversity over time doesn't produce infectious disease benefits. It doesn't result in a reduction in the disease burden for people living in that country. Not what we would have wanted to see if we wanted to see the dilution effect upheld. So, what do I want you to take home from this? Disease responses aren't general. Each parasite is different. Different drivers are important for different parasites. We can't just press on one driver and expect all of the infectious diseases, or even most of them, to respond. But if we were going to press on just one driver, it wouldn't be nature. It would be urbanization. Seems really counterintuitive, right? We think of cities as teeming cesspits of disease, but cities also bring people into close contact with doctors. Having people in cities makes it easier for public health agencies to distribute things like vaccines or treat for mosquitoes. It makes it easier for municipal central utilities to provide clean water and sanitation. So cities actually might be good for people's health, and that's good news in an increasingly urbanized world. Nature does provide disease services. Like, we have seen that there are at least some infectious diseases, some parasites, that decline in burden in response to conservation. But nature also provides disease disservices. Our data suggests that conservation is not going to provide blanket protection against infectious disease. Conservation might be useful on an individual disease basis, but we need to be aware that it's equally likely to exacerbate disease transmission. And we need to be able to anticipate and avoid that, because the absolute last thing that we want to do is a conservation project that gets people sick. There's been so much hope in the ecology literature that biodiversity could yield the consistent ecosystem service of disease control. The work that I did with my colleagues suggests that that hope is unwarranted. Instead of insisting on generalities about conservation and disease, we need to look for individual opportunities for win-win outcomes. Individual meaning on an individual parasite species basis. These might exist, but they need to be screened for and targeted. They're not likely to be common across diseases or across contexts. So obviously, I don't want you to take what you've learned today and use it as justification to cut down a forest. Ecosystems offer a lot of services, but control of parasitic diseases is probably not one of those services. I'll see you in the next video.